is Ellen Friedman. I'm a principal technologist with MapR and a committer for Apache Foundation projects, also an O'Reilly author. And I'm here today to talk to you about how to build a global data fabric and why you might want to do that, what that could do for you. And I want to start with the fact that a very big idea, when it's executed well, can have an enormous reach. And in fact, to take this example, we'll reach all the way into space. I want you to think for a moment about a problem, a challenge, of how you study the world's oceans and the world's atmosphere. And take something as sounds simple as measuring the temperature of different ocean currents around the world. Now, years ago, the only way you could do this is to actually go out on ships, take a sample, measure the temperature, record that data. The ship moves to a new place, take another sample. But when you think about the size of what you're trying to measure, the measurement ends up not being very meaningful because by the time you get to another location in the ocean current, everything's changed. You can't have basically a comprehensive view of what's happening. And so the big idea behind doing this better is to be able to do it on a global scale, to be able to do it from remote sensing from satellites, but it couldn't really go forward until certain things had to happen. Technology had to be developed to put those sensors up on satellites. A satellite called CSAT was launched in 1978. Was going to operate for a long time, taking sensory measurements. I see some heads nodding out there who remember that. Sad thing is, it only operated for about 105, 106 days, and then it went dark. The good news is they collected so much data, they were still able to have the basis for huge insights. The bad news was, back in those days, that was a lot of big data and too much really for the computing power at the time. And so it was actually several years later before real inroads were made to be able to study the data and draw conclusions that really began to roll out during the 80s. And that's when we really began to understand the ocean systems, the atmospheric systems on a whole global scale. And tremendous advances happened to the point that recently, with this rash of horrible hurricanes that came through this summer, Hurricane Harvey hit the southern part of the U.S. and dropped a phenomenal amount of water on the Texas coast. The only thing that was surprising about Harvey is that some people were surprised because it did exactly what it was predicted to do. The path, the duration, the amount of water, the sophistication to be able to predict these systems now is amazing. And the reason is a combination of a big idea, the right technologies, and all that put together. Now, in some cases, you don't have to wait for the technology to be built when you have a big idea. Sometimes the pieces are already there, and the only thing missing basically is the big idea. And that was true for another big data use case, one that really showed the power of aggregating data to be able to study the world's oceans, currents, and winds. But in this case, it all took place in the 19th century. There was a sailor in the U.S. Navy named Matthew Maury. He injured himself as a young man and could no longer go to sea, and he ended up with a desk job. Now, you would think that's where adventure stops, but for him, it's where it really started, because he was a man who could have a very big idea and execute it well. He noticed that there were boxes and boxes with these dusty old books, logs from ship captains. Someone would go on a trip. They would take various measurements and also write down random things like whether the rum was holding up. Come back, dump the book in a box, the book in a box, and just leave it. Now, there were thousands of these books, and any single captain's log had very little value, very little information that was usable unless there were real questions about that particular trip, like what happened to all the rum. But Matthew Maury saw the value in the fact that there were these huge number of observations, of measurements, time series measurements really, of ocean temperature, ocean currents, wind temperature and direction, atmospheric conditions, and that with his team, if you could painstakingly extract all that information in aggregate, Big data can answer questions that you couldn't have answered before, and that's what they did. They produced these amazing winds and currents charts. This really mattered because on these long sailing voyages, if you didn't make the trip in the time you needed to make it in, you could end up running out of water, running out of food, basically die. This is a life or death situation, and also one that has to do with competition for getting to port with your goods in time. Anyway, they produced these charts. Nothing like this had ever been there before. Huge value in aggregated data, and really all he added is the idea. The pieces were already there. Now, when he first did this, nobody paid any attention to them because the users didn't have the insight, the innovation, to see how they could be used until this one ship captain made a run from Baltimore, Maryland, the East Coast to the U.S., down to Rio de Janeiro and back, shaved off a month on the transit time, and when somebody comes back a month early, everybody starts to notice, and after that, everybody wanted to use these charts. It made a huge difference in how navigation was done. Building a global data fabric just sounds like glitzy marketing words, but it's not the words. Call it anything you want. It's the idea behind it. It's a huge idea. And when executed well, it can make a tremendous difference in how your business works, how your research works, the kinds of questions you can ask. Because I'm talking about a big idea that executed well can take the potential promise of big data and now put it into real value that comes out in production settings. We're talking about things that are pragmatic, not just theoretical. And so let's see how that works. One of the issues, and people have been talking about this for some years now, is to try to aggregate data to break down unwanted silos. I'm sure everybody in the room has heard people talk about building a data lake, and that certainly is a fine idea in the sense of aggregating data. But the problem is sometimes data is just thrown together in a data lake. People can't find the data in the lake. It's not very practical. It's hard to use it. So it's hard for that potential to come to real fruition. I'm talking about something that accomplishes that same thing, but the data fabric is built differently, and it's really talking about bringing data where you can have a comprehensive view of the data. You don't have to bring it all in physically to the same place. Use the data where you need to use it, put computation where you need it, do that with a huge variety of teams, and do it in a way that doesn't require a massive overhead and additional system administration. We need systems that are fast. We need systems that have flexibility, that let you respond in an agile way to changes. The world will change. Whatever system you build today needs to be able to change rapidly with it. And so I'm talking about doing something different than the data lake and what I'm calling a data fabric. If you're working on a larger scale, a global data fabric, something that adds that flexibility and agility. Now, there are a number of different, this is the big idea, there are a number of different technologies and steps that need to go into building this, but a central thing, I think there are more than one way to do it, but the way that I recommend, a central thing, is to do this based on a stream-based architecture. Use event streams, stream transport, at the heart of your architecture rather than just in specialized projects. And by moving to that stream-based, stream-first architecture, it lets you build this data fabric in a way, think of again, the analogy, the threads, the warp and woof of a fabric. If you know where the data is, each different thread, you can go in, access the data, exactly the data you want, wherever you want it, from wherever you are, okay? So you can get access to the different threads, and you can control access to the threads. You can easily administer who has access and who doesn't on a thread-by-thread basis. But the key thing here is that, like a fabric, all of these work together as a single thing. So it can be administered together, one big system administration, under the same security. This can be done on-premises, in cloud, as a hybrid. And that's the difference. This is what brings it into a practical setting in real-world settings where teams can work together with data and really make this work in a way to bring value. So today, business has to happen basically at the speed of life, wherever you are. And it's not just speed, it's also access. It's using multiple data sources, multiple data types. And simplicity is the key here. Not a bunch of separate component technologies that are connected, brought together through connectors, but it works best if you can simplify that. The more that you can work together with a single foundational technology really opens up all the different systems that you build on top of it. I say global data fabric, and that's what a lot of people are looking for, but it doesn't have to be global for a data fabric to still be of value. If you're working at one site, that sense that you still have multiple data sources, a comprehensive view of the data that you want, easily accessible by different people, still gives you the same advantage. It's simply that for a lot of people, being able to access data wherever it is, use data sources wherever they are, makes a difference. And so you should be able to do either as appropriate for your situation. It's also true that a lot of people right now are looking to work in a cloud environment, either completely or for part of what they do. Often it's the need for a huge amount of computation that drives them to want to look at a cloud environment. We find that it's useful to do this, set up your data fabric in a way that you maintain cloud neutrality. That gives you a lot of flexibility, a lot of openness. And doing that also lets you basically optimize between workloads that really are appropriate for the cloud when you have a big burst, workloads that are really cheaper to do an on-premises way. So that kind of hybrid architecture is really the best of these worlds. And again, this is having built a data fabric really gives you the opportunity to do this. Now, we've talked about a lot of these aspects already. I do want to just mention that it's really important to also, for a lot of systems, to be able to bring data processing, computation, right to the edge, say the edge of an IoT situation. You have IoT sensors. So this is a lot of data moving fast, a lot of locations. You want sometimes to have the option to do some processing right at that edge, capture the data at the center, do some processing, send those insights back to data centers or multiple data centers. Sometimes you want to send all of the data back. Sometimes you want to send a processed version. Again, having that flexibility to do what's appropriate for your project. But having this ability to do edge computing is really changing for a lot of different situations, the way businesses can move forward, the way humans can make decisions, and in some cases, computer-assisted decisions. It's not just faster. Again, big data isn't just big. It's qualitatively different. It lets you ask different questions. In the case of speed, it's not just faster, sometimes to do this edge computing, but it changes the way people can interact with data. They can make decisions and do it in a time scale that lets them come back with a second question and a third question fast enough that it's happening as events are happening. So it's a very different thing. It's also really important to be able to maintain flexibility in data, not just in streams. People use NoSQL databases. You don't have to do as much refinement, as much processing of data. You want to be able to use unstructured data. You want to keep some data in raw form, because the choices you make to optimize data for, say, a particular database, a particular project, may be fine, but it may not be what you need to do next month and next year. And so having that flexibility that you don't have to make every decision about how you're going to use data at the point that you first put it into a database, for example, is a different style of working, but it's a huge difference. It really, again, gives you flexibility. Now, all of that's good in the abstract, nice, powerful idea, but can this work in the real world? Does it have real-world impact? And so I'm going to give you some examples from, I do consulting for MapR technology, so those are the customers and the technology that I'm most familiar with. And so I'm going to give you some examples how people are already doing this and the kind of impact that it's had on what they're trying to do. Let's start with this. This is a customer that has an online service. I won't say what, but they have a particular need, and not an unusual one in business, as that is that they need to collect metrics. They need to do it fast because of the speed of their business. They need to get those metrics back to central centers for processing because, among other things, they use these metrics for billing for their customers. So this needs to happen fast and accurately. They have a global business. They have a huge distribution, geo-distribution of these data sources, and they need to have developers and data scientists scientists developing the applications that will analyze the data for, to look at the behavior of customers, but also to be able to do their billing. And so this customer, this already was a MapR customer, and they were using MapR in aspects of, just take a side, MapR is a data platform that is a single technology that has a distributed file system that's a real file system. It's fully read-write. It's hugely scalable. It has a NoSQL database that, again, is not just connected. It's not running on a separate cluster, but it's literally part of the same code. It has a stream transport that uses the Kafka API. All of these have open APIs, but again, rather than running on a separate cluster, the MapR streams transport is part of the same code, the same technology, and everything can be run basically in the same system, the same cluster. So they were already using the system. They started taking advantage of stream replication, geo-distributed replication, to handle their log metrics. And just by making that change, really now moving into using it as a data fabric, they came back within 3 months, and they said they now felt like they had a year of development time in the bank. And so this is the kind of real impact. What happened is that their developers no longer had to deal with things in terms of logistics of data that could easily be handled at the platform level. They didn't have to build it into applications. It made administration easier, and it made their work be able to focus on what they were actually trying to do. Edge computing is another example where this happens. A number of different customers already taking advantage of this. Let's take the example of medical customers who are trying to do computer-assisted, AI-assisted analysis of various scans so that the physician can get that information back quicker. The final diagnosis is still a human decision. The doctor, she or he, gets the information back from the scan with basically augmented understanding, but all this can be done in a central data center. So analyzing a scan where the results might not come back for 24 hours, now that time can go down to basically less than 15 minutes. Think of how that changes the interaction of the physician with the patient, the decisions about therapy, how all this moves forward. So it isn't just faster, it's qualitatively different because of that difference in speed. So if this sounds good, the question comes, how do you actually build a data fabric? And the important things are the capabilities that you want. I know, as I said, I'm using examples from MapR because it's a technology that was designed to be able to do this. You could put different components together and build it in different ways, but it's the capabilities that you want. That's what you should look for in whatever technology you choose. I do think using a stream transport at the heart of the technology is key. People often come to streaming data or stream transport because they have some real-time application and they want a kind of to queue the data before it comes to the application so they don't drop anything. But with the right kind of stream transport, Apache Kafka has the right style. MapR Streams uses that style in the Kafka API, and I'll tell you a little more about what I mean by the right style. It gives you the opportunity to use streaming at the heart of a larger architecture where you can actually have durable messages, set a long time to live, and that gives you an event-by-event long-term history. And it also lets you realize out of that data a kind of what's the status at the moment view. You might put that optimized into, say, a search document or a database. In the case of medical records, that might be your electronic medical records. It might be a facilities report relative to some machinery. Your long-term event-by-event stream could be used, say, for an audit or an insurance audit. So it's not just that real-time reporting that is the value of going to this stream-based approach. Now, why I say this style gives you a big difference is that it's not broadcasting. The stream transport, Apache Kafka, MapR Streams, they're not broadcasting the results to the consumers. They're able to support data, use data streams from multiple data sources, and you can have multiple consumers or consumer groups, but the events are not being broadcast to the consumers. The consumers subscribe to that. And the difference, that's a huge difference. It decouples the producers from the consumers. It decouples the consumers from each other. You can do this with low latency, and meaning the message is right there to be used when it's needed. But here's the key thing, is that the consumer does not have to be online, at the time the message arrives. It can be added later, and that's a huge difference. That gives you that decoupling. And that is the reason that this kind of stream transfer, this kind of architecture, can actually provide the lightweight connectors that give you a microservices style approach. And so the key capabilities that these two technologies have that make that possible is that at huge scale, you have both high performance and persistence. You need durable messages. You need that message to be there even when the consumer is not online. It does support a microservices kind of approach, and in this kind of approach, this is for an example for fraud detection, by simply inserting a message stream between the model and a database where you're storing and updating results. Now that output message data can be shared by a number of different groups, including the people who are building this fraud detection system. When they want to try to roll out a new model, they can test it independently in a production setting without interfering with the actual production model that's going on. I already mentioned to you that the MapR platform has all of these technologies put together, but another aspect that's really useful for building a data fabric, and especially a global data fabric, is with MapR you actually have a global namespace. So a developer can access data wherever the data lives, again, around the world, on-premise and cloud, and this really changes the way people can work with data. Using stream replication, basically, the developer can be on site, the developer can be at a remote location, it all looks the same. And so you get, again, that separation of concerns, it frees up developer times, it makes administration work much more smoothly. We see this in real-world cases. Another customer, an ad tech customer, has their inventory are basically ads that have to be kept up to date. And this business goes very, very fast, but you have multiple centers. Locally, the centers are doing bidding and keeping billing records for the sale of these ads. But the inventory is a global inventory. And so by putting that inventory in streams, those streams are replicated globally, basically. It gives them the ability to run this business at the speed that it needs to run. We also see similar things in financial services with trades. It's very helpful to be able to explode this up and have a huge number of topics so you can query very efficiently into individual topics. And this gets back to the idea of a global data fabric, having those individual threads where you can find exactly what you want. You don't have to do this just with streams. Being able to have bidirectional multi-master table replication is also very useful, where you're trying to capture data from a data source and get it into a table close by so there are no interruptions, but be able to share that in an accurate and consistent way across data centers. Now, I just want to touch with one last idea here as we're closing. We've talked about the importance of handling a lot of this at the platform level, but another aspect is how you organize the humans who are doing this work. I think a lot of people here will be familiar with the concept of DevOps. And we're seeing today that it's helpful as people extend that concept further to include the data-heavy roles of software development. People become data engineers, of data scientists, and the difference is a difference in communication, so that cutting across these skills, you break down skill guilds, you have people who are working together as small teams. They're focused on a common and practical business goal, and so they can communicate more effectively. This is faster time to value. It makes them more flexible, more agile. We find that people coming in, people who are software engineers and developers, are excited about the idea of becoming data engineers, of being part of these projects, including machine learning projects. Now, machine learning is coming into every aspect of our life. You hear a lot lately, and rightfully so, about deep learning, about AI. These systems are really becoming mainstream across businesses and certainly in research settings as well. And an example, a very new example of this whole combination of a stream-based architecture being used to build a global data fabric is in the example of how you can handle machine learning logistics for projects that are being built, where the models are being built by a variety of tools. We find that people like to have multiple good tools, TensorFlow, Caffe, MXNet, H2O, whatever tool they're using, whatever application they're building, they still need to be able to handle data from many sources at scale, to be able to handle the output data, to manage huge numbers of models. You don't just have a single model and deal with that. And you want a way to have models ready to deploy immediately, roll back if you need to. And there's basically this concept called a rendezvous server that's based on the kind of architecture and data fabric that we've been talking about. With Ted Dunning, who's MapR's chief application architect, he's here in the front row. We've written a book recently called Machine Learning Logistics, and it talks about these ideas of how to handle, using a data fabric, the logistics of managing machine learning projects. It talks about the rendezvous architecture in detail. We will have copies. We're going to do a book signing with free copies at the MapR booth at 12:30 today. Ted's going to do a small talk at the booth at about 3:15, going much deeper into this concept of how this plays out in machine learning, and I hope you guys can join us for that. And just a final plug, please continue to support women in technology. It's lovely to look around this room and see how many women are here, but this isn't just to help women, it's good for society. It's good for everybody, so please do it. And this is One Woman in High Tech. I say thank you very much for your time today.